Today we also invited as our keynote speaker Professor Carsten Carlberg from Polish Academy of Science Research Institute on animal reproduction and food research. Carsten today is with us. He is a German biochemist. He worked for several years in Switzerland in division of Roche. He also was teaching in Kuopio in Finland. Now he takes a position of area chair in Institute in Olsztyn. Carsten, good morning. Thank you very much for joining us for
Adam,
this event, and the floor is yours.
Yeah, Adam, thank you very much for the introduction. Can everyone see my slides?
Yes, we can. Thank you.
Okay, good. At the moment, I think it is not too many people there. I see just 8 people participating, but I hope a few more people are joining. Anyway, what I want to talk about, as you can see here, prevention of cancer by lifestyle changes, and I want to focus to some extent on the impact of our epigenome. So, first, I would like to kind of play with some numbers concerning the burden of cancer and its prevention, with the hope that I can introduce or provide a background to the other talks that are following to mine. And I guess all of you know, but maybe not know the detailed numbers. Worldwide, about 60 million people are dying everyone from the 8 billion that we are. And if you categorize this by the cause of death, cancer is number 2 with nearly 10 million deaths. You may ask why I have color-coded it here, and it is that everything which is orange is at least indirectly related to failures in our immune system, and that is something that I want to also highlight, and I see the connection to epigenetics. So cancer being kind of the cause of death or the reason of death, the number 2 worldwide. Then if you're going for further numbers, and that is for what exact reason we are dying. So the same 60 million people, but now looking on what was the major reason for dying, and that is high blood pressure, which is primarily related to the cardiovascular diseases. But number 2, 7.1 million people are dying worldwide every year due to smoking. Because that is, if you just think about what is the number 1, what we should do fighting against cancer, simply ban all smoking worldwide. Would save every year 7.1 million people's lives. But then we have, and that is probably more the focus of the meeting here, a number of food-related issues. That is high blood sugar, obesity, high diet, high sodium in diet, low in whole grains, that means low in fiber, and so on. I don't want to read now the whole list to you, where you again have millions of individuals dying due to the one or the other thing. And here it is very obvious that as much as you can avoid simply to smoke by don't smoke, is you can avoid obesity, just move more, eat less, and you can also very simply change your diet and having less sodium in the diet. This is a very simple kind of advice where you may say, hey, we were talking here maybe about fancy food and fancy food addition. A very, very simple thing is just to avoid salt in the diet. And if you prepare the food yourself, you have it under control. If you have some packed food where you don't read the detailed ingredients, you may just take a lot of salt in every pizza or whatever. Nothing against pizza, I like very much pizza, but there is a high amount of salt in there. just as one example. So here we have, with this list, we have a kind of immediate to-do list, what to change. We don't need anything fancy. We basically just have to think about the composition of our diet, and we would have a lot of prevention of disease. Of course, not only cancer, all different types of diseases. But if we switch back to cancer, here are data from the US from 2020. The total number of females and males having every year a diagnosis of cancer. And that is if you are taking the total population of US together and would put it over 80 years, meaning that over lifetime, every second person will get a diagnosis of cancer, 1 in 2. Yeah, this is a tremendously high number. Fortunately, the number of people dying from cancer is not as high. And you see here the comparable number. It basically says that only some 30% of the people getting cancer dying from it. Of course, also you know that this is something depending on the definition, most cancers are followed up 5 years. So you mean you survive the cancer when you are not dying within 5 years. Otherwise, you're out of the statistics of most cancers. So going now a bit more to the details, the molecular details of cancer. Cancer is a multi-step process and mostly takes time. So the initial steps, just a few cells are overdoing some overgrowth. Then there is a bit more overgrowth, but still being on the level of benign tumor. And then we have a small cancer. All this process can take years or decades. And really dangerous cancer gets when these cells forming the tumor have acquired properties that allow them to move out from the cancer to form metastasis. So this is kind of the point of no return. And my honest opinion is, if you reach this stage of metastasis, this is not something you can heal. That's my personal opinion. So the main point is, I mean, you can give people extra lifetime by doing some treatment, but the main point is preventing that cells in our body getting to that stage, which is, from my point of view, a point of no return. So therefore, we have to think about what are the reasons that cells having apparently doing this change and accumulating certain type of properties, the so-called hallmarks of cancer. And the reasons for that are basically 3 elements. We can have bad luck that we carry something in our germline, something we got from our parents, some mutations, but this is affecting to 5, maximal 10% of cancer patients. So the very most of cancer patients, they have either kind of bad luck. Bad luck is meaning that due to the fact that certain tissues like skin, colon, blood, that means bone marrow, have to grow to the maintenance of our body, there will be a number of mistakes in the replication and the growth of the tissues, and that causes mutations. But another aspect, and that is, from my point of view, of not only my point of view, it is from the data, 70% of all cancers are dependent on lifestyle choices. Of course, the choice if we are smoking or not smoking, what we're eating, how much we are moving. Yeah? These lifestyle choices are translated with the help of the epigenome. And here I come to my favorite topic, epigenome, to changes, to possible hits if these are bad lifestyle choices, to that finally can drive ourselves from normal to this aggressive cancer you can't survive. So the main point here is most of the cancers can be prevented, 70%, and they are largely dependent on our lifestyle choices. So as the title of my talk already says, we can and should prevent cancer basically as early as possible. So I understand the focus of the meeting is to help cancer patients. So basically people having already a diagnosis of cancer and convince them to change their life, to eat something different so that the progression of cancer is not as fast and that they have extra lifetime. Yes, and in every stage of life, even if you have cancer, changing of lifestyle, if possible, if the people still have energy for that, is definitely beneficial. But as you probably will all believe, is that if you are even having a lifestyle that is preventing cancer, you never ever get cancer. So it's not only the focus of people having cancer, from my point of view, but the focus is of everyone. So everyone should be also customer or can be customer of a lifestyle, of a diet that is preventing cancer. So this is finishing the first part of my presentation. Then I want to make you a clearer link to epigenetics. So what is epigenetic? Epigenetics is basically the packaging of our genome. The genome is the dark line here, which is in complex with proteins. The proteins are so-called nucleosomes, and we have area of accessible chromatin, and we have area, there's also dense area here in this nucleus. This is an electron microscopic picture of the nucleus, where we have no access. So basically, I have here a model, hopefully you can see it, a model of the chromatin, a pearls on a string, which are either accessible or inaccessible. I can hide the epigenome in my hand, then I have heterochromatin. And this is epigenetics. It's basically chromatin, the accessibility of our genomic DNA is the physical expression of the epigenome, as the text on the right side says. So we have different levels of the epigenome, and I don't want to go to any unnecessary detail, but the epigenome is found on the level of DNA methylation. Epi, by the way, means on top. So it's on top of the genome and not changing, not mutating our sequence of the genome, but adding something like a methyl group to cytosine. It also the packaging of the chromatin and the three-dimensional organization of the chromatin, as well as certain type of messages which are written on the back of these histone proteins. So this at least five different levels distinguish if we having regions of our genome which are not accessible, so-called no-go areas, and regions which are accessible. So this is the major regulatory aspect of the epigenome, deciding which part of the genome is accessible and which is not accessible. And we can have that also as a model with an epigenetic landscape. And I try also to represent it here. We have a landscape like the Tatra mountain, not too far away from Kraków. So we have here at the summit of the mountain, this is a stem cell, which is then differentiating to the 400 different tissues and cell types following the one or the other valley. And what does a cancer cell do? A cancer cell is starting with a differentiated cell, and this differentiated cell is kind of climbing up this valley, and then by that getting extra properties, getting properties similar to stem cells. And that makes, unfortunately, cancer cells very dangerous because they don't do then these changes in an ordered fashion as normally happening during embryogenesis, but in a very disorganized way. And that is creating then these dangerous cancer cells. So if we summarize concerning epigenetics, and here we have only 4 master examples of tissues, but we are formed, our body is formed, I already said it, by 400 tissues and cell types. We have in each our cells the same genome. And here I compare 2 different individuals having at the one or the other position a different genome. We are in overall in 1% of our sequence different. But we have variants in the epigenome in each of our tissues. So if you remember the details of my of my title, epigenomes. Our body is formed by at least 400 different epigenomes. And now you imagine that one of these tissue is turning to cancer. There is then a change of the epigenome in that individual and contributing. So as there is the change of the DNA in form of mutations, copy number variations like amplifications and deletions, translocations. So the typical things one knows well how on the DNA level cancer is created. We have also on the epigenome changes, in particular the methylation, either less methylation, hypomethylation, or its special position hyper, that means increased methylation, and other types of activation, epigenetic activation and silencing, comparable to the activation of oncogenes and the suppression of tumor suppressor genes that happens in the tumorigenesis process. So one example, hopefully a bit illustrative. If you go back to my model of the epigenetic landscape, we have here different type of valleys. These valleys are here represented here at the end. So we have at the bottom of this landscape where terminally differentiated cells are, we having left and right rather high mountains and barriers where normally the cells are not climbing up. So of course, this is a model. This is not really a landscape in our cells. It is just saying there is a barrier that normally due to the epigenome cells are behaving well. They are staying kind of here on the bottom of the valley and do not move. But what happens in cancer is that the epigenome is changing, and changing is a response of lifestyle changes, of kind of misbehaviors in case of cancers, eating the wrong things, and so on. Then we change the epigenome, and that in the model looks like as if we would have flattened the valleys, and suddenly the cells are able to move left and right and have in this way the chance to do some rather unusual things, and therefore are not behaving correctly. This is also what you can see here on the right side, a multi-step tumorigenesis from normal tissue via adenoma to carcinoma. Here 10 different cells are shown, and you see when the cells turn to cancer cells, the level of methylation is in this case drastically decreasing. In a more specific model, as a concrete example, in a normal cells, we have certain regions of our genome where we have heavy methylation. These regions, often in repetitive sequence, the so-called junk DNA of our genome, representing nearly 50% of our genome, is methylated so that it doesn't get activated, while important genes like p53, a tumor suppressor, should be activated in all of our cells. And what happens in cancer cells? What happens when the epigenome kind of is collapsing, the borders are collapsing? That means that the regions that normally should be not active are getting activated. The white heads here indicate no methylation, and the rate of methylation is drastically decreasing. So we have hypomethylation. And then regions are getting active that we don't want to have active, while on the other side, genes like p53 or the control regions, the promoter of p53, gets methylated, and the guardian angel p53 is then not accessible, it's not transcribed. So in this case, we don't have a mutation of p53, we just inactivate its expression. And that is, of course, leading to the contributing to the multi-step tumorigenesis. And now I want to link epigenetics with nutrigenomics. And what is nutrigenomics? The very simple type of definition is that from the diet that we're taking up every day, we have many molecules, nutritional molecules, who have the potential either directly activate a transcription factor or chromatin modifier, or do that after a metabolism in one or the other way. The molecule is changed a bit. For example, vitamin D is changed in 2 steps to 1,25 dihydroxyvitamin D. It's the active form of vitamin D, which is directly activating a transcription factor. All these nutritional compounds activate a single transduction cascade, and at the bottom of the single transduction cascade, there are again transcription factors or chromatin modifiers. So chromatin modifiers are those enzymes who are changing, for example, the methylation status of our DNA or of the proteins on which the DNA is wrapped around this histone proteins. And the net outcome are changes of physiological conditions, for example, the ability of growth. So we have nutritional compounds who may inhibit growth, that is expected, that there is no overgrowth in our body, or we may have also molecules who do the opposite and unfortunately stimulate growth. So there changes in the epigenome is supporting the cancer and providing extra hallmarks of cancer. So the proteins that are handling the chromatin, remember, chromatin is the complex of the genomic DNA, the brown line here wrapped around the protein. This is chromatin, and this chromatin is handled by proteins. These are the chromatin modifiers. And these chromatin modifiers, most of them are enzymes. And enzymes, you may know, can be modulated by small molecules. And I here have a couple of plant-based molecules coming from green tea, soy, grape, cocoa, and curcuma that are affecting the activity of these enzymes, and by that affecting directly our epigenome. So by, for example, using curcuma as a spice instead of salt, we not only provide get a lower blood pressure and provide any other problems that salt is causing our body, but the main point is higher blood pressure, but we are also getting a nice taste replacing the salt with curcuma and have in parallel an effect on our epigenome, a beneficial effect, of course. So plant-based molecules are often having a beneficial effect on the epigenome. So here we have a list of do's and don'ts for cancer. So decreasing risk, definitely it's physical activity, then the fruits, vegetables, and so on, grains, whole grains, so fiber, and of course a number of compounds like vitamins. I'm working a lot on vitamin D, so I would like to highlight vitamin D. Definitely you should take care, in particular now in the winter, on the vitamin D level. So, and a number of downs that you have on that side is overweight, obesity, processed meat, aflatoxin coming from fungi, and then salt as a driver, red meat. I guess all these are common knowledge, what is good and what is not good. So what should be prevented on this side and what should be recommended. And what I want to bring in here is that a number of these molecules are able to directly modulate the epigenome. So this is the mechanistic understanding of how the epigenome and how our lifestyle is affecting the epigenome and acting counter cancer. So one example I still want to give you, and that is the link of obesity and cancer. And I guess this is also something we will have to discuss later. A lean person has in its adipose tissue a limited number, a limited size of adipocytes and also respective microenvironment of immune cells like macrophages of type 2, which are beneficial. This tissue is not inflamed, but an overweight or obese person has not only larger adipocytes and a higher amount of adipocytes, but the wrong microenvironment of macrophages of the type 2. And these macrophages of type 2 are pro-inflammatory. So the outcome is that a number of pro-inflammatory cytokines like tumor necrosis factor, interleukin-6 and others are then not only locally produced in this adipose tissue, but they're also distributing through the whole body and affecting other tissues. And this can drive cancer. So here on the right side, you see that a normal tissue in the multi-step of process going to aggressive tissue and effects from outside. Are inflammation and increased lipid levels, insulin signaling, fat mobilization. So effects that are normally just mentioned in the context of cardiovascular diseases, but they are also driving the tumorigenesis process, and therefore they are dangerous. So again, a very simple advice is lose weight, be normal weight, reduce the inflammation in the tissue so that this further driving process to carcinogenesis, the process is inhibited. So that brings me to one of my favorite slides and saying now on a broader perspective, not only in the perspective of cancer, but of course in the context of this speech and primarily in the context of cancer, that we have in all our cells an epigenome, which is influenced by many different aspects. And one of the influence is the lifestyle. Another influence is our immune system, which basically talks with all cells of our body. And that is also epigenetically programmed. It's an issue I would have to give an extra talk about. But basically, the immune system is programmed. And then we have the counterpart of what we're eating and the metabolism of these molecules and the inflammation, which is in many different tissues, or can be many different tissues of our body, in particular if we're overweight or obese. And also with normal aging, the level of inflammation is increasing. So this is affecting the epigenome of the individual cells. And if these are cancer cells, the cancer is pushed. But it has also an effect on a number of different diseases we are not discussing today, but you see this is a more global picture. So we have the triangle of some genetic predisposition, but this is maybe some 20% of all at max. We have lifestyle decisions which work via the epigenome or via the immune system and are contributing to the remaining 80% of the risk. So it really means what we are doing, what we are eating is affecting the risk of getting many diseases, within one is cancer. So you may ask from where all these nice pictures came. Hopefully you like the pictures. They are coming from the different books that I have written on nutrigenomics, on cancer biology, on immunology, on epigenetics. And yeah, this would be recommended for reading. And yeah, I thank my team, which we started a couple of months ago here in Olsztyn, and of course the EU for funding of our Welcome to project. So that's my presentation, and I hope I stayed in time.